Namaskar, this is Nayan and I welcome all of you to my new lecture series. Students, in my previous 3 videos, I solved a total of 15 problems from SLET 2024 Physical Science paper. Today also, I will continue this journey by solving another set of 5 problems. So, without further delay, let's get started. Problem number 16. This problem number 16 is asked from analog electronics topic, and according to this problem, we have an electronic circuit like this. In this electronic circuit, A and B are two identical transistors. Here the supply voltage is 5 volt. The resistance at the collector terminal of transistor A is 100 ohm. The base emitter voltage for both these transistors is 0.7 volt. We need to find out the amount of current flowing through the transistor B. Option A 48 milliampere, option B 45 milliampere, option C 43 milliampere, option D 40 milliampere. Here the correct answer is option C. Now let me show you how option C is the correct answer. Students, let us first distribute the currents at different branches of this electronic circuit. Suppose I amount of current is coming from the supply voltage. This I amount of current is splitted into two parts at this junction. Suppose I1 amount of current is flowing along this path and I2 amount of current is flowing along this path. Since A and B both are identical transistors and base emitter voltage for both these transistors is 0.7 volt, so therefore I1 must be equal to I2. First let me write these points. Solution. Since A and B are identical transistors and VBE is 0.7 volt for both these transistors, so same amount of current, will be flowing through both these transistors. Thus, I1 must be equal to I2. Now, let us apply Kirchhoff voltage law to the loop 1. Suppose this is loop number 1. So, after applying Kirchhoff voltage law to this loop number 1, we will get 5 minus 100 into I1 minus 0.7 equal to 0. Here one important point is that this I1 is almost equal to collector current of transistor A is almost equal to emitter current of transistor A, because the base current for transistor A is almost negligible. Okay? Now, after simplifying this equation, we will get I1 is equal to 4.3 divided by 100 ampere, which is equal to 43 milliampere. Since I1 equal to I2, so the amount of current flowing through transistor B will be 43 milliampere. So the correct answer is option C. ठीक है? Now I want to give a clarification here. According to me, this is the best explanation for question number 16. But still, if you have better explanation for question number 16, please leave a comment here. Next, problem number 17. This problem number 17 is also asked from analog electronics topic, and according to this problem, which of the following semiconductor diodes is not a differential negative resistance device? Option A, Zener diode. Option B, tunnel diode. Option C, GaN diode. Option D, IMPET diode. Students, before solving this problem, first let me define you what is a differential negative resistance device. This differential negative resistance device is characterized by a negative slope over a certain range of voltage. That means over a certain range of voltage there is a decrease in current due to increase in voltage. First let me write these points. Differential negative resistance device is characterized by a negative slope, that is di by dV less than 0 in the IV curve over a certain range of voltage. That means over a certain range of voltage there is a decrease in current due to increase in voltage. So if we look at the IV characteristics of Zener diode, tunnel diode, GaN diode and IMPET diode, then we have seen that except Zener diode, all the other diodes have a negative slope over a certain range of voltage. That means there is a decrease in current due to increase in voltage for this type of diodes. So therefore this Zener diode is not a differential negative resistance device. So the correct answer is option A. All the other diodes, that means tunnel diode, GaN diode and IMPET diode are differential negative resistance devices, and this region is known as the negative resistance region for tunnel diode. This is known as the negative resistance region for GaN diode, and this region is known as the negative resistance region for the IMPET diode. Okay? Next problem number 18. This problem number 18 is asked from atomic and molecular physics topic, and according to this problem the number of splitting levels of 2p orbital is option A 1, option B 2, option C 3, option D 4. Here the correct answer is option C. Now let me show you how option C is the correct answer. Solution: for 2p orbital principal quantum number is 2 and orbital or azimuthal quantum number is 1. So, therefore, the possible splitting levels of the 2p orbital is given by twice L plus 1, which is equal to 2 into, here the value of L is 1, 2 into 1 plus 1, which is equal to 3, and they are 2 px, 2 py and 2 pz. So, the correct answer is option C. Next, problem number 19. This problem number 19 is also asked from atomic and molecular physics topic, and according to this problem we have to find out the correct answer out of these 4 options. The problem says that the sensitivity of ESR or electron spin resonance increases with option A, increasing temperature and decreasing magnetic field strength, option B, decreasing temperature and increasing magnetic field strength, option C, increasing temperature and increasing magnetic field strength, option D, decreasing temperature and decreasing magnetic field strength. Students, before solving this problem, first let me define you what is sensitivity of ESR spectrometer. Students, the ability of ESR spectrometer to detect small amount of paramagnetic species is known as the sensitivity of ESR spectrometer. First, let me write this statement. The ability of ESR spectrometer to detect small amount of paramagnetic species is called the sensitivity of ESR spectrometer. This sensitivity of ESR spectrometer strongly depends on strength of magnetic field and temperature. Number 1, if the strength of magnetic field increases, then the energy separation between the spin states increases. As a result, the population difference between the spin states also increases. This actually leads to strong ESR signal and improve sensitivity. So, we can say that due to increase in magnetic field strength, the sensitivity of ESR spectrometer increases. Number 2, if temperature decreases, then population difference between the spin states increases due to reduced thermal excitation. This also leads to strong ESR signal and improve sensitivity. That means due to decrease in temperature, the sensitivity of ESR spectrometer increases. So, the correct answer is option B. So, the sensitivity of ESR spectrometer increases with decreasing temperature and increasing magnetic field strength. Next, problem number 20. This problem number 20 is also asked from atomic and molecular physics topic, and according to this problem, when a monochromatic radiation of wavelength 4358 angstrom passes through a certain sample, Stokes radiation is obtained at 4458 angstrom. The anti-Stokes radiation would be at option A 4258 angstrom, option B 4260 62 angstrom, option C 4308 angstrom, option D 4310 angstrom. Here the correct answer is option B. Now let me show you how option B is the correct answer. Students, before solving this problem, first let me write some important points. Important points. Number 1, always try to solve this type of problems in wave number scale first. And finally write the result in wavelength scale. By using the relation nu bar is equal to 1 by lambda. ठीक है. Number 2, the positions of Stokes and anti-Stokes lines on wave number scale are given by, suppose this is the wave number scale, nu bar scale, and we assume that this is the position of exciting line whose wave number is nu naught bar. So this is the position of exciting line. So the position of anti-Stokes line will be nu naught bar plus delta nu bar, where delta nu bar is the separation between exciting line and the anti-Stokes line. ठीक है, anti-Stokes line. Again the position of Stokes line will be nu naught minus delta nu bar. So this is the position of Stokes line. Again delta nu bar is the separation between exciting line and the Stokes line. Solution. Given the wavelength of exciting radiation is 4358 angstrom. In terms of wave number scale, the wave number of exciting radiation will be 1 by lambda naught, which is equal to 1 by 4358 angstrom. After simplification, we will get 22946 centimeter inverse. Again, according to this problem, the wavelength of Stokes radiation is 4458 angstrom. In terms of wave number scale, the wave number of Stokes radiation will be 1 by lambda s, which is equal to 1 by 4458 angstrom. After simplification, we will get 22431 centimeter inverse. Therefore, the Raman shift will be delta nu bar is equal to nu naught bar minus nu s bar, which is equal to 22946 minus 22431 centimeter inverse. So, after simplification we will get 515 centimeter inverse. So, therefore, the position of anti-Stokes line will be nu as bar is equal to nu naught plus delta nu bar, which is equal to nu naught bar 22946 plus 515 centimeter inverse. So, after adding these two terms we will get 23461 centimeter inverse. In terms of wavelength, the position of anti-Stokes line will be 1 by nu as bar. We know nu as bar is 23461 centimeter inverse. After simplification we will get 4262 angstrom. So, therefore, the option B is the correct answer. This is all about today's video, and I hope that you have learnt a lot from this video.